All right. We're going to be talking about some specific energy today, and that ties into the assignment you've got due at the end of this week. The first part of the assignment, though, steady uniform flow, that's all related to Manning's equation. So that assignment's due on Friday. The next phase of your design project is due on Friday the 20th, and we'll talk a little bit about the design project today before we get into total energy, specific energy, and critical flow. So the next phase of the design project is you're going to be sizing the pipes. And I did the demo in class on Friday, kind of refreshing your memory on how to use water gems by solving that same example that we had previously looked at with the Hardy-Cross method and spreadsheets. The basic idea is that if your pipes aren't large enough, then there are going to be consequences. That if you can't deliver all the water that's needed within your network, then the industrial demands mean that the businesses have to shut down. If there's not enough water for the green spaces, then that's going to wilt and die. People need the water for drinking and for cleaning. And so your sizing at each of the locations, the design condition should be the larger of either the maximum daily demand plus fire or maximum hourly demand. And so you've just gone through that activity to find out what's the flow rate required at each of the junctions where there's a green arrow on the map. Now, what you have to do in the next phase is make sure that the pipes are big enough to ensure that when maximum demand is occurring, none of the junction pressures go below 240 kilopascals. And then during static conditions, meaning when there's no demand, so you set all the flow demands to 0, then you have to make sure that the pressure doesn't go above 850 kilopascals. So it's during the high demand times that the flow rate will be low, because when water is flowing through the pipes, there are losses. And there won't be any losses when there's 0 demand. The conditions will be static, the pressures will be high. Now, it would be easy to do the project and have acceptable pressures if you just made all of the pipes really large. But that wouldn't be economically efficient. And so you have to minimize the pipe diameters. And remember the assumption that part of what's affecting the pressure is not only the losses through the pipes, but also the elevation at the junction. And so the map that you have includes contours, elevation contours. And so when you're typing in the data for each junction, one of the data pieces that you have to put in is the elevation at the junction. And so you can either use the surface elevation, or if you even want to be a little more sophisticated than that, assume that the pipes will be 1 meter below the surface, and then it's just a uniform buried depth for the entire network. Now, the first phase of how much water is needed, the second phase of optimizing the pipe size, and also you're going to have to optimize the location of the pipes, because the question is, what's the most efficient layout and pattern for the location of the pipes to connect all of the junctions together. Another part of the puzzle, though, is where to put the reservoir. How high on the hillside to place the reservoir. And I'll show you a map in just a minute as an illustration, but the higher the reservoir goes up on the hillside, the more pressurized the network is going to be. But if the reservoir is too high on the hillside, then the system is overpressurized during low demand periods. So if the reservoir was up by the spring, for example, at the top of the hill, then that would mean that there's too much pressure inside of the network. So you're going to have to also be looking at the placement of the reservoir. So the optimization is getting the pressure within the guidelines and trying to find the smallest possible pipe that will make it so that you're just barely satisfying that requirement. And so really be relentless and ruthless in trying to get each of your junctions as close to 240 as possible. If I look at your network map and you've got pressures all over like 300 and above, then that'll tell me that most probably there are certain pipes in the network that could have been downsized even further. So just barely satisfy the requirements, because remember, what you're sizing the pipes for is this rare thing, this the situation that is the hottest day of the year where there's a fire going and there's also a football game and the factory is running at full tilt and it happens to be in the middle of the evening when people are washing their clothes and flushing the toilet and doing dishes. And so it's okay if you barely provide the minimum during that very rare occurrence. That means that all the rest of the time you'll have far more than the minimum pressure. If you need some additional pointers on how to use water gems, there's a couple of videos and you'll be able to click those links in the notes, I think. I believe that water gems in the more recent editions has a built-in PDF printer that you can use, and so you don't necessarily need PDF Creator. I think that by default the generating a PDF is going to be available to you without. But in case you need to install a PDF Creator, what it basically does is it sets up a printer that if you select that printer, then it just generates the file rather than sending a paper out of the machine. Okay, here's the example map that I said I'd show you. This is an annotated map, and these are the annotations that need to be in the two maps that you provide. And so you can notice that the diameter of the pipe is specified, the length of each pipe is identified, the flow rate through each pipe, and the person who generated this map made it in such a way that all the information wasn't on top of it, of each other. You know, the vertical offsets that you can program when you're setting up the annotations will put it above the line or below the line, and so this person did a good job setting it up so that it was really clear and that none of the information was on top. Sometimes you'll have to manually drag the labels to side, but you know, that's not too hard. You'll notice that at the junctions, the flow rate that's coming out of the junction is annotated, as well as the pressure at the junction. Yeah. And then for the reservoir, they've identified the elevation that they set the reservoir to. And so this is the annotated map for the demand, where the peak demand design condition. And so in this case, we'll see that they have pressure at this junction, 275 kilopascals. I don't see the hospital, 290, housing project, 267, but no place is the pressure below 240, but also the pressure isn't really high. And so they've done a good job kind of demonstrating the optimization that we're looking for. Jeffrey, do you have a question?
Do we enter in two maps where it's the high demand and low demand?
That's right.
Okay.
Yeah, I want two maps so I can see what the network is doing when you've got this peak demand, and then what's the network doing when there's no demand, like overnight when there's so little flow being drawn out of the system that effectively you have static pressure. Now, this was from a year where I told the students where the pipes had to go. Like, for instance, I told them that the pipe had to go through junction J, but now you have the freedom to connect the dots however you like to minimize not only the pipe diameter but also the pipe length. And so, for instance, if I saw this map where all these dots had been connected, I'd say, well, why even bother having pipe G to the golf course, H? Because there's only 3 liters per second going through GH. Why not just eliminate that pipe and provide the water to location H through IH? You've got 70 liters per second going through that pipe, send another 3. And then, for instance, if this was this year, I'd look at junction J and I'd say, why send the pipe through a location where there's no demand? And so it would be better to connect the dots directly between the hospital and the housing project. So there's multiple places where you don't necessarily have to take the flow to a junction where there's no water being taken out, and you can have the pipe dead end. And there are practical reasons why it's advantageous to have a loop rather than a dead end, but let's assume that in this case the dead ends are just fine, and so occasionally those lines would have to be flushed out if it was a real world scenario. If there's lines that dead end and they're not getting much use over time, you sometimes have to send the fire department to flush the water out of the hydrants, otherwise the lines can get clogged with sediment or iron and stuff. But any questions about the map or the next phase of the project? Okay. Well, let's talk about open channel flow. We have a channel, and let's just use a rectangular channel because it's easy to do the calculations for rectangular channel. If we had a rectangular channel that was 4 meters wide and we're sending water through it, let's say that we're sending 10 cubic meters per second through this trough that is 4 meters wide. And we could have it be a really steep slope, or we could have it be a really gentle, mild slope. And depending on how steep the slope is going to affect the depth of flow. So that's the basic idea that we're going to be looking at on the next slide. But before we do, I want to introduce the idea of specific energy. Specific energy is a little bit different from total energy. Total energy includes the elevation above a datum, whereas specific energy is saying we're only going to measure how much energy there is in the system above the channel. And so you can see it's the flow depth and the velocity head. So those are the two terms that go into specific energy, whereas the total energy would also have a delta Z, where your delta Z is some distance above a vertical datum. And so the other way that we can write velocity head is q squared divided by 2ga squared. And so instead of, if we don't know the velocity, sometimes it's more convenient to write the velocity head in terms of the flow rate. Okay, so this is just the concept of specific energy. So what if we send 10 cubic meters per second through this rectangular trough at a variety of different slopes? Let's say, what if we sent 10 cubic meters per second through a really steep channel, and it was so steep that now the velocity is going 10 meters per second. And we also do an experiment where we send that same 10 cubic meters through a really mild slope, and it's so gradual and flat that only 1 meter per second is the flow velocity. What this table does is it says for a certain velocity and a certain flow rate, you could calculate by definition what cross-sectional area you have to have in order to achieve a velocity of 10 meters per second. And so we've rearranged the continuity equation here, and in this column you'd have q divided by the velocity. So obviously for the top cell it's going to be 1 square meter. And if you know the cross-sectional area, you can find the depth of flow by dividing the area by 4. So if the area is 1 square meter, that means the flow depth would have to be 0.25 meters, because we're dividing the area by 1. Now look at the other extreme. If the velocity is 1 meter per second, then that means that the area is going to be 10 square meters. And so then the depth would be 10 divided by 4. So let's say that we calculated for a whole different variety of velocities, and we achieved all these different velocities by changing the slope for the channel. So we have a lot of different cross-sectional areas that correspond to increasing versus decreasing velocities. There's a corresponding depth for each of them, and then we could calculate the specific energy with this formula, where we're adding the depth and the velocity head. So q squared divided by 2ga squared. All right, so I've done that for all of these, but I'd like you to try it out just for the 3 that are indicated with the arrow. And actually, for sake of time, just do the top one. Calculate the cross-sectional area, the flow depth, and the specific energy if we have a velocity of 8 meters per second. Okay, so we should expect to see a cross-sectional area of 1.25 square meters. And then if we divide that area by 4, because that's the width of the channel, we can get the depth of flow would have to be 0.313. And then the energy is going to be the depth plus the velocity head. And so we can calculate the velocity head as q squared divided by 2ga squared. Or since we have v, it could just be v squared divided by 2ga squared. So for every different flow depth, you'll notice that there's a different specific energy. So it's the same flow rate, and it's the same roughness of the channel, the same channel width, but what we're doing is we're just by increasing and decreasing the slope, we're forcing the flow to go at either a lower velocity or a higher velocity. The thing that's interesting to look at is that the energy is high at one extreme. Now, when the depth is small, like where is the energy? And it can be in two places. It can be in the depth or the velocity head. So in this top row, where is most of the energy? Is most of the energy in the flow depth or in the velocity head? If we have 5.3 meters of energy, how much of that energy is in the depth? 0.25. So the vast majority of the energy, when you've got a shallow depth, is in the velocity head. Look how big the velocity is. And so, you know, v squared divided by 2g, if you're squaring 10, that's 100. Now you divide by 2g. So of this 5.347 meters, 5.1 of it approximately is in the velocity head, and only a little bit is in the depth. Now consider the other extreme, down here on the bottom row. If the velocity is only 1 meter per second, we know that of the specific energy of 2.551 meters, most of that energy comes from the flow depth. And so there's going to be very little energy tied up in the velocity head. And this is an important point. Does everybody get what I'm saying when I am kind of telling you the different places the energy is? Because specific energy has two terms, and so we have to think, where is the specific energy at a given depth? Is it in the velocity or is it in the flow depth itself? There's also this point of minimum specific energy, and you may be wondering why I picked such an odd velocity and why it ended up being this odd depth. There's a reason. I chose that odd velocity because I knew that that was the velocity that corresponded to the lowest specific energy. And so this point of the lowest specific energy is an important dividing line that we'll look at graphically. So we can take this information and graph it. This is a graph of that same data, flow velocity versus depth. And this graph's not that important. It's the next graph that's more important. If we graph the specific energy versus flow depth. This was velocity versus depth. And so the trend was, if you had a high velocity, you had to have a low depth, and a high depth was a low velocity, but each one of these points all had the same flow rate. Remember, the flow rate was 10 cubic meters per second for all of them. So if we instead graph the specific energy on the horizontal axis and the depth of flow on the vertical axis, this figure has a lot of significance, and we'll return to it several times through the semester because it shows us important things. This minimum point, minimum specific energy, corresponds to something that's called the critical depth. And so we label that Y sub c. So back to the table, the minimum specific energy gives us this depth of 0.861, and that's the critical depth. Critical depth and minimum specific energy. And if we think of it as the slope is what's controlling the depth of flow, remember that the low depth of flow, like when it was really shallow, was when the water was moving fast. you had a big velocity when it was shallow. Like if you take that the trough that the water's flowing through and make it really steep, then it's going to be shallow as the water goes down that slope. So below this dividing line, below the critical depth, these are regions where the flow is supercritical. And above the line, that's called subcritical, where the flow is moving at a lower velocity. And it's a little confusing. Sometimes people forget which is which, because you'd think below the line would be sub and above the line would be super, but it's actually the other way around. Supercritical flow is corresponding to high velocity. And so the high velocities are going to be with the lower depths. So all of the factors contribute to flow, like the roughness, the geometry, but it's the slope that determines the flow depth. And if we want to classify whether the flow is supercritical or subcritical, then we can calculate the specific energy and compare it to the minimum. The other important thing that we can draw from this figure is the alternate depth. And what that means is that for a certain amount of specific energy, you could have either a shallow depth or a deeper depth. And so there's two different depths that have the same amount of energy. And if we go back to the table from this previous slide, let's look and see if we won't have any that are exactly equal, but we'll have some that are pretty close. Like, look at this one. When the flow depth is 0.625, the specific energy was 1.44. When the depth was 1.25, then the specific energy was 1.45. And so just a little bit less than that depth would give us the same specific energy as when the depth is 0.625. And so two different depths, same specific energy. When water goes through changes, sometimes it will seek out that alternate depth. So alternate depths, that's important terminology. It means two different depths that have the same specific energy. We'll talk later in the semester about hydraulic jumps. And when water goes through a hydraulic jump, it's going to jump up to the alternate depth that has the same amount of specific energy. Any questions so far? So here's the rule that you need to remember. If the depth of flow in a channel is less than the critical depth, that means you have supercritical flow. If the flow that you're observing is deeper than the critical depth, then that's subcritical flow. So here are those rules. So the slow-moving water is going to give you subcritical conditions. The fast-moving water will give you supercritical conditions. And so you'll have fast-moving water when it's shallow, meaning less than the critical depth. You'll have slow-moving water when the water is deeper. There is a top width that can be calculated when the flow is critical, and we call that B sub C. We've been talking about a rectangular channel so far today, and the width of the channel isn't going to change with the flow depth. But if it was trapezoidal, then the flow width at the top would change. And so here the top width is always 4. But if you had a trapezoidal channel and the depth is going up and going down, then this top width, which is capital B, would be changing. And so B sub C is the top width when you have critical flow. So you may remember that in an earlier assignment you classified the flow regime. And your classification was supercritical or subcritical. And that was based on something called the Froude number. Here's another version of the Froude number. This they're showing as Froude number squared is flow rate squared times the top width divided by gravitational constant times area to the third power. So if you wanted to find Froude, you'd take the square root of the right-hand side of the equation. The flow regime criteria that you applied before is when the Froude number is less than 1, it's subcritical conditions, and when the Froude number is greater than 1, it's supercritical, and if it's exactly equal to 1, then that just means that it's critical flow. So those are the flow regimes. Now, hydraulic depth, I think we've talked about before how it's the ratio of the area to to the top width. And of a rectangular channel, if you have the top width times the depth is area, so B times Y is the area, and then you divide it by B, the critical depth for a rectangular channel is just the hydraulic depth is just equal to Y. And that same thing is true if you have a very wide channel, even if it's trapezoidal. So if you have a channel that is trapezoidal, but it's more than 20 times wider than it is deep, then the effect of these side areas become insignificant, and so that the hydraulic depth of a very wide channel is just its flow depth. But for any channel that isn't rectangular or very wide, then you can calculate the hydraulic depth that you'd need for this Froude number equation by the area divided by the top width. Okay, 148. We don't have time to do this calculation, but I do have time to show it to you. So that's what we'll do. This is the same graph that we've seen before, specific energy. This is the 10 cubic meters per second that's going through our rectangular channel. All right, so this is a refresher, when we have the shallow depth, so the depth is less than the critical depth. So the critical depth is 0.86. So when the depth is less than 0.86, is the flow supercritical or subcritical? I wonder why I bolded supercritical. Maybe it was a hint. All right, so it is supercritical, and the Froude number we can calculate by having the flow rate squared multiplied by the top width divided by G. The cross-sectional area is 1. Now, that area, remember, is the width, 4, times the depth, 0.25. So that's where the 1 square meter comes from, but we have to cube that. So the Froude number confirms what the depth also indicated. The depth told us it was supercritical, and so does the Froude number. Now, the other bullet point, we're looking at the other extreme. What if the depth is greater than 0.86? So the flow depth is 1.25. That's more than the critical depth. So when Y is greater than Y sub C, that means you have subcritical conditions, and the Froude number confirms it. The Froude number that we calculate is less than 1, so that also verifies subcritical flow. We are out of time. I will see you on Wednesday. Hope you have a great day.